I've actually got 3.
Oh, right.
Yeah. All of them are pretty good. So, and it depends on the type of current you want.
Oh, okay. Right.
So that's my first question.
Right. What are we talking about?
Microcurrent.
Microcurrent.
The microcurrent budget edition, I guess.
Okay, so we're talking about the one that goes into a doodad case.
Yeah.
Is that the one we're talking about?
The fancy 9-volt battery one? Is that
Yep.
what you're Yes.
Because there are 2. There is a potential microcurrent gold Mark II.
Yep.
But, yeah, I don't know what direction to take that.
What is that? An option? What are the options? Like high bandwidth?
Oh, that'd be, higher bandwidth, higher, it might even have conversion built in. So, like it might have a high resolution converter built in.
Yeah.
I don't know which direction I want to take it.
Well, in a month or two, you'll have because my product has an inbuilt converter, but it's not a current thing. But it's like a multimeter, but it has an inbuilt converter. So if you go the other direction, then if you sell that, you have both.
Right.
So if you take the, what's it called? What was the budget edition? If you take the budget edition.
The budget edition.
I don't know what to call it.
Yeah, well, no, neither do I. I haven't thought about it. Because the background to that is we're also doing a project. It started out, still going. We're doing a project for a preamp.
Yeah.
Right, to measure low noise, power supply stuff, crap like that. So it's going to be like a similar sort of
there you go.
little thingamabob that plugs in your scope. Just a little add-on times what, 20 and times?
Yeah, 50 and
50?
20. Yeah,
50 and 20.
Here, don't we?
What do we have?
You have the actual product, don't you? The assembly.
Oh, the prototype you did. Yeah, it's still on that bench somewhere. Yeah.
Here it is.
Yeah.
So we've got a prototype here.
Yeah, but we didn't really. Yeah, it wasn't that great.
No.
Anyway. So yeah, the thing is, you came up with this funky case, and as often is the case, pun intended. As often is the case can make the project.
Yeah.
The case can make the project. You come up with a funky case idea, you can go, ooh, that change. You design your product around the case.
Yeah.
Not necessarily, right, I need these features, and then you just treat the case last. The case can actually drive your functionality, and it kind of does in this case. So what we were going to do is, we're still going to do it, is the front end, for want of a better word.
It's been seeking a name.
Micro front end, Anyway, it's a micro preamp or whatever is probably a better name.
Yeah.
And times 20 times 50 amplifier, just a niche product for low noise measurement and stuff like that on a scope. So you get lower range on your scope. And you came up for a real funky case.
Yeah.
So which used a 9-volt battery. Because we resigned ourselves to the fact that we couldn't, when we're looking at the amps for this,
it had to be above.
We're not presenting to camera. Why am I presenting to camera? We're supposed to be brainstorming between ourselves and just have the camera running just in case we want to release this someday.
Sorry about the sudden paradigm shift.
Yeah,
or whatever it is called.
No, anyway.
Anyway.
So we were looking at amps and, choose certain amps, and they need 10 milliamps or something they need?
Yeah, and they have a high voltage range, right? So it required minimum rails.
It requires, exactly. So, but it was the current. Even once you get over a few milliamps, that's more than what you can get with coin cell, right? The CR2032s and stuff.
Yeah, and the battery life is just dead.
Yeah, it's just dead. They're not designed for that. So 9-volt was a good solution because it gave us the high voltage. We didn't have to dick around with multiple C's and multiple AA's or AAA's in series. You would have needed 4 at least to get your 6 volts because you don't want a boost converter.
Yeah, because it's just noisy.
Yeah, you don't want a noisy boost converter inside of a preamp. That's designed to measure tens of microvolts.
Yeah, you're constantly see 100 kilohertz in the scope. And this is so weird. I just can't get rid of the signal.
Oh, wonder what's causing it. You dickhead. You put a boost converter, right? So nice clean battery.
Yeah.
And so 9-volt was the only option, really. It was the logical option. And then, so you designed a funky case that just fits in. It had press contacts and it, I don't know.
Yeah, it had the
hard to explain
battery case on the back.
Yeah.
And then you just slot it into the case, and then there you go.
Yeah. Yeah. So anyway, it's pretty funky. So that's a product on its own, which probably doesn't need. We've got a chip. We've got some die-cast boxes. We'll build up a prototype, make sure it all works, and then if it does, it's just a matter of integration into a into a thing.
Yeah, the solution.
Right? Yeah. So do you want to take those with you and actually build it up? Or?
Yes.
Right. Yeah, because you're waiting. You've been waiting for me for months, and I haven't done it. Although. Yeah, I'm not sure which one of these you want. Have you got like B and C connectors? You can.
I got plenty of B and Cs, but they're all in that style. But I can solder them and clamp them and whatever.
Whatever. Anyway, anyway, take a die-cast box. Yep.
Won't fit in my bag anymore.
Oh, really?
Yeah.
Well, that's full.
Yeah.
Holy crap! What's in there?
Yeah, open it. That's my Surface.
Oh, your Surface tablet, right? With a Raspberry Pi.
It's like the perfect size.
Yep.
And then
right.
And then everything.
And then all your little power adapters and power brick and.
Yeah. Backup
is there a mouse?
And,
you got got a moose in there.
Yeah. USB drive, backup storage.
Right. All that sort of stuff. Right. So it's a computer bag rather than a.
Yeah.
Is it designed for that?
No, but it fits so well.
All right. Anyway, if you haven't seen it, there we go.
It's tiny.
It's a Black Wolf.
Yeah.
Yep.
It's great.
All it needs is some drainage holes on the bottom and take a canyoning.
Yeah. Add them in.
Which we'll have to do this summer.
Yep.
We'll have to do it.
Definitely should. That'd
Once
be fun.
my knee is hopefully.
Yeah, I've never been canyoning.
No, he hasn't. Yep.
Yeah. And I love rock climbing, so I probably love that.
You'll enjoy it.
Yeah.
Yep. Although you'll probably go, there's nothing. It's like it's just scrambling down a creek.
It's
That's
fun.
Pretty much all it is. You know. So anyway, we were.
Yes.
So we does So it's micro front end, and then I got to thinking that case might be able to be reused with something, and so I thought a microcurrent that just has more limited range than the current one.
Yeah.
6-volt battery is ideal because then we can get a full 6-volt. 9-volt battery is ideal because then we can drop out at 5 volts or 6 volts or whatever. So we get maximise the use out of the battery.
Yeah.
And we get a full 5-volt output swing as well.
Yeah.
And it doesn't need to be.
Well, we've got 5-volt positive if you want to sacrifice the negative rail.
That's the thing. I was going to sacrifice the negative rail.
Yeah.
Because most uses for the microcurrent are to measure current consumption in a single power rail solution, right? It's not it's not being used as an AC amplifier. So really, you just have to ensure that you wire it into your negative rail. And I don't think that's for a cut down product. I don't think that's a big deal.
Didn't always do that, did it?
Yeah, it's always done that. Yeah, this table wobbles because I didn't put minimal bracing on it. I only put bracing at the top. I didn't put bracing at the bottom. Aha! There you go. All right. So, yes, I think sacrifice the dual rail capability. I'm pretty sure the existing op amps, the Max 4239s, go down, sense down to 0 volts. So,
well, we can have a negative 0.5 volt rail or something.
Shouldn't need to.
Yeah.
I think it'll sense down to ground. That'll simplify things.
Yeah.
The problem with the microcurrent and current measurement in general is dynamic range, right?
It's just low.
It's just low dynamic range. Even if you have a 12-bit
and is that
or
especially with like low burden? Like
no, it makes no difference whether it's low burden or not. It just makes no difference because you're trying to measure. Sleep current of a micro. The primary example is the sleep current of a microcontroller, which is microamps, right? In fact, I was just doing a video the other day.
Could be almost sub.
The pick is 10 nanoamps in sleep. It's 300 if you turn on the RTC, right? 300 nanoamps, right? So it's got to go. So you've got to measure that with some degree of precision, and then you've got to also measure hundreds of milliamps. Right, because so
that's where auto-ranging came in,
and that's where auto-ranging. But this is where the niche product comes in. The microcurrent goes up to amps, right? It can go up to several amps. What is it? 2 amps. It's limited by the output voltage. It's limited by the output voltage range of the swing. 2 amps, and so how many orders of magnitude is that? It's massive. Even if you go from 10 nanoamps or 100 nanoamps to a milliamp,
Yeah.
That is still better. That is still a larger order of magnitude than you can measure with like a 5.5 digit meter, right? You need like a 24-bit converter to get the dynamic range possible, right? So unless you hook it up to a large dynamic range
or amp to get access to more bits as it goes lower.
Or amplifier, but that's the problem, and hence the auto ranging.
Yeah.
Right. So the whole like getting large dynamic range is extremely difficult. But then again, so is auto ranging. So the auto ranging.
Auto ranging has more problems because you're not doing a storage device.
Do we have it?
Because like you're not creating a storage device, are you? You're creating
storage device.
Well, if you're not converting to your volts, then your auto range on the scope's going to look like this.
You're losing. Yes, but that's the whole idea.
It's going to be discontinuous.
Right, that's the whole. Well, so, yes, but that's all right. That's right. Now the problem with auto ranging is if you've got a chopper amp. I'm assuming that's in shot. If you've got a chopper amp has a internal oscillator. It's got an internal oscillator, typically tens of kilohertz, 10 kilohertz or something, and V plus and let's say ground. Now the problem is if your output swings high like this and it goes all the way up and saturates at V plus, okay, so if you overdrive the input,
it latches.
Well, it takes time to recover.
That's what
recovery
time.
And so what you get, so it goes up like that, which is fine. If you're viewing this on a scope, you might, you can do two separate measurements. You can do the measurement when it's high, like this, and then you want to do the measurement when it goes low, but you want to keep the same range switch position on your microcurrent, right? So that's fine. You can overload the thing and you won't hurt the amplifier. You won't blow it up or whatever. You'll just get more burden voltage, right? So you'll just get, your burden voltage on your input here is just higher, right? But it's already low.
But it doesn't translate.
It doesn't matter. So you can overdrive your amplifier, no problems. But when you overdrive it, and then when you recover like this, instead of going back low, you've got a recovery time, TR or whatever it is, and that's specified in the data sheet. So I'll tell you it's 3 milliseconds or something, whatever. And you actually get the oscillation at the frequency of the chopper amp.
I didn't realize it was the chopper frequency.
It's the chopper frequency. It's not anything to do with the dynamics of your layout, your capacity of load, or anything like that.
So I guess you have to keep it away from the rails. You have to.
You have to clamp it. So if you're either overdrive, this applies in both cases. If you're overdriving the thing, if you've just got a microcurrent like you've got now, you can overdrive it like this, but you'll have that recovery time, and you will see some oscillation in there, and you think, oh, that's part of my product's doing that, when it's not. It's the microcurrent. You can't avoid it. And you'll have the same problem also in auto ranging as well, because if you're trying to swap between amplifiers or swap between gains, then you could, if you accidentally saturate it. So what we have to do is clamp it somewhere. Well, we've got to have a clamping circuit, and the clamping circuit has to go on the input. The clamping circuit has to go on the input. So it's going to be down in the millivolt region because our burden voltage is low, right? The amplifier is times 100.
Yeah.
Or if you've got multiple stages, the first stage might be times 10.
Yeah. Right?
So, but still, our burden voltage here is low. It's typically tens of millivolts.
Yeah.
Right? So, okay, so it's going to probably be in the hundreds of millivolts range.
Diodes have sufficiently low leakage. Some silicon.
Yeah, but it's got to be pretty sharp.
Yeah.
Yeah.
True.
Although, no, low leakage doesn't matter. Low leakage doesn't matter in this case because this is a low impedance.
Yeah.
This is like,
I'm so used to the front end.
No. Two different designs here.
They've got the opposite. They've got the opposite problem. Yeah.
So that's 10 ohms. I hope everyone can see that here. Anyway, it's pretty crap quality footage, whatever. Sorry. May not even be in focus. Actually, it probably won't be. Sorry. Anyway, so Where was I? Yeah, so it doesn't matter because it's a low impedance source. It's a low impedance source.
Yeah.
So leakage doesn't matter. So you need some sort of clamping, and that clamping has to be at a fairly precise voltage, you know, like within 50 millivolts or something. You know, it's got to be, you know, tens of millivolts maybe. So a diode may not cut it, and you may not luck upon...
It's like an active
And
clamp.
that changes with temperature too.
You're talking like an active clamp.
It's got to be some sort of active clamp.
Which
so
are okay, because the
yeah.
ringing on the active clamp exists, but you're clamping. So it's...
Oh, yeah, no. Don't worry about that. Yeah, no.
Yeah.
Yep. That's fine.
Yeah.
So, yeah, the whole
As long
idea
as
is stopping your amplifier overloading,
Because
saturating.
This one, the clamping
Yeah.
amp will, whatever kind it is,
Yep.
will have ringing, but
Yep.
when it's ringing, this amp is in control, because it's got...
Oh, yes, yeah. The amp is not going into oscillation, so you're not
Yeah.
going to get the oscillation due to the internal chopper there.
Yeah.
So, yeah, that's that. That was kind of a non sequitur, really. Anyway, that's part of the design that needs to... If I was to redesign the microcurrent, I would do this. I would actually, regardless of which version of the microcurrent it is, I would add clamping to stop overdrive of your amp. And of course, that, you know, people might think, oh, look, my product's gone up to this level here and it's clamped. That must be the level that I measure. That's the measurement of my product. You've got to actually be very specific that your
Look, it
spec...
peaks at 5 milliamps.
Yeah. Yeah, when it's actually drawing 10, right? You have to make sure that your spec, and you put it in big asterisks in your data sheet for your product and say...
Maybe with an example
do
of a
not,
sine wave.
Yeah, yes. Yeah, you have to explain this to people.
Yeah.
Do not, if you go over this spec, then it might look like your product is doing the right thing, but your measurement is going to be incorrect.
And what's even especially more, like if someone's logging on a scope, which is what I do when I'm doing power monitoring.
Yes, yeah.
I don't look at the waveform all that much.
No.
Because I would have to look at it for 10 hours.
Right.
I get the data, I integrate the whole waveform, and then we get some energy, right?
Right. Well, see, so here's the thing with...
For power, not current.
Right. Not sure if you can see that.
Yeah.
But here's the thing, if you're looking at this on a scope, which I want my new version of microcurrent to be, right, it'll be like that, right? So you'll have a huge current up here, and this will be orders of magnitude difference between there and there. And you want to measure this tiny little thing down here. Usually this will be down in the noise, so you just set your scope to trigger at that point. So after you do this measurement first, you measure your high current first, and then you turn up the range on your scope and trigger at a different point and measure the low current. So it's it's not as fancy-pantsy. Now, but it's doable.
Functional.
So it's a solution. Yeah, it's functional. Now the other thing is that if you wanted to get really fancy, if you had an auto-ranging system, which auto-ranges, which was what we need to talk about, so then you can leave your scope on the 1 voltage range, like 1 volt per division or whatever, and you get 5 divisions, then you need to know which range it's in, at which point in time you need to know. So it's almost as if the product needs a second output that you then hook into the second channel of the scope, and it gives you a level or a marker. It tells you its level. Idea. And I was thinking this the other day.
Multiply.
That's what I was thinking. That's what I was thinking the other day.
Yeah, that's a good idea.
Yes, I was thinking that if you outputted a precise, a voltage, a known voltage, like it has to be DC, that's it. DC voltage for each range, like 1 volt represented.
If it's times 10, you have a divide by 10 range.
Right,
If
yes.
If it's times 100,
it output a volt, and then it output 100
100
millivolts, and it output 10 millivolts or whatever.
So they multiply it to get a SI unit.
Yes, and then with the math function in your scope, you could possibly, I have not yet tried it, but maybe you could multiply it and get, but you can't do that to the scale factor of the scope. Like some scopes, you can change the probe input and say, I'm using a current probe and it's milliamps per volt, right?
Yeah.
And stuff, you can't change that with the math function. So, anyway. But the good news is that it tells you. It tells you when you're doing it, although you should know because of the clamping, right? You should know what the clamping voltage is, and then, although maybe an easier way is microcurrent has a second output which simply says, I'm clamping. I'm overload, like an overload output.
That's a good. That's a damn useful thing.
Yeah.
Because in the case of the way I do energy stuff, I could just say, is this ever greater than 0?
Right. Yeah.
If it is, do it again.
Do it again. Exactly. So you have an overload output on the scope. So you have 2 B and C's on there, and one is your signal, one is a overload output. This doesn't apply to the micro.
So you have one range that's clamping and one that's not. You subtract the two, and if it's ever greater than 1, that's an overload. If it's ever greater than 0, it's an overload.
You get an output. The good thing about this clamping circuit, you get a digital output from that. Boop, boop.
Oh, okay, yeah.
You get a digital output directly.
Oh, you mean a full, like, hard...
talking about a 5-volt TTL output.
What's it called? Crowbar. Are you talking about crowbar clamping?
No, crowbar shorts.
Yeah, that's what I thought you meant.
No, it's just a detector. It's basically, this is just an overload detector.
Okay, yeah.
Crowbar's not the right word. Crowbar is...
crowbars are short. I thought...
Short,
because I assumed that signal was driving a FET.
Oh, right. No. Oh, well, it could. Well, actually, you're kind of right. It is kind of crowbarring. Yes, because you've got to actually clamp it before it goes in. There's many different ways you can skin that cat, and that's not what we want to talk about, really. But yes.
Yeah, they all work,
right.
so
yeah,
it's
you
okay.
Could. Yeah, you could physically clamp it to a level. Anyway, so an overload output is probably the go.
Yeah.
So if I was to design a new microcurrent gold Mark II, it would have 2 outputs.
I'm curious, why didn't you go to platinum? That's the normal...
Right, microcurrent, I might go to
That's
microcurrent
the normal
platinum.
progression.
Okay, right, all right, gold, yep. Silver, gold, platinum.
Right.
Right.
What did you start with?
Just microcurrent.
That's good, that's fine.
It's gold because I got some gold-plated connectors and I thought, I'll make it...
We can't afford platinum.
Right.
So who can, right?
Actually, platinum's currently cheaper than gold.
What?
Yeah. Yeah, no.
Should
it is.
Buying?
No, gold's currently in Aussie dollars. Gold's about, fluctuates about 5% a day at the moment.
Is that because platinum's low or was gold's high?
Platinum went gold. Platinum went down to $900 an ounce, or $750 an ounce or something in the last year. Platinum went down. It plummeted.
Should I buy?
Platinum's. Yeah. Hardly anyone plays in the platinum space.
Perfect.
Anyway. So, yes, we need an overload. So I would have an overload output.
Yeah,
like
that's
an
useful.
symbol. Yeah, I would have an overload output because the new microcurrent, I think, should be a tool that's designed to more specifically measure product current consumption. Whereas the current microcurrent is just overcome the burden voltage on a multimeter. That was its original intention, and it works really well.
Yeah.
Right. Hence why it did the positive and negative rail and everything else. It's just designed because your meter does positive negative. The microcurrent did positive negative.
So would you want bandwidth as well then for with this guy? Because you do get harder.
Yeah. Bandwidth's hard. You've got to trade off accuracy for bandwidth.
Yeah.
So
but where is it? This guy is like right in the sweet spot. That op amp we've got.
Did we lose it already, or have you put it in your bag?
It would be in my bag, actually.
Okay.
Yeah, that thing seems like in the sweet spot, and the expensive one was...
Yeah, but no. But the problem is, you see, it's got to have an offset of... The reason the current op amp is chosen is because it's got to have an offset of 0.1 microvolts.
It's got a chopper.
Yeah, it was. Yes, that's why you use a chopper, because it effectively eliminates...
Yeah.
But not all... I was going to say those keys might
I know.
Put them in your bag.
Yeah.
That's the thing with choppers. But even choppers aren't perfect, right? Yeah, you use it because a regular op amp, 2 millivolts offset. You got to it's in the order. It's in that order.
Yeah. Chopper
amps, you go into the order of microvolts. But whether or not there's a big difference between whether or not it's 10 microvolts, 50, or it's 0.1. The current one I've got is 0.1 nominal, maximum of 2. Depends on temperature.
Microvolts.
Bullshit, yeah. But it's nominally 0.1, and you do get that because it's got a gain of 100. So if what's 0.1 microvolts times 100? Come on, math boy.
10.
10 what? Micro.
Yeah.
Yeah. So if you hook the micro up to a meter, you'll find there should be, on average, a 10 microvolt offset.
Yeah.
There when you're feeding no input.
Yeah. And practically you'd expect a bit less, right? would it be?
No. That's typical. No, that's typical.
Actually,
That is actually typical. In fact, you might get a bit worse than that.
Okay.
Because your input offset multiplies by your gain. So if you've got a times 100 gain amp, it multiplies.
Okay, so we want...
That's why a multi-stage is better. Doing all your gain in one amp isn't as good as doing it in multiple stages. Although it kind of is, but the math works out a bit better if you use multi-stages. Your offsets still add up, but not by the same. I don't think by the same.
So if you're, when you said you're not doing a bipolar type supply, are you saying precision rectify, or are you saying ignore negative rail?
Ignore negative rails. If you go negative, it doesn't work. It clamps. Okay. It can't blow it up, obviously. If you plug it in backwards, you don't want it to blow up. But, so you want some protection, but apart from that, no, it just simply doesn't work. Okay. Yeah. Yep. Because, I think it should be, because I want to transition it to a product that wasn't, that no longer just overcomes the burden voltage of a multimeter. That's what the microcurrent gold can still be used for. In fact, I can still sell it for that. Yeah. But the new one should be more targeted towards measurement and monitoring of product current consumption. Yeah. So you don't need negative rail. Why? I'd rather have a bigger dynamic range. Yeah. In a single direction. If you're dumb enough to hook it up backwards, well, you're not going to get any result out of it, right? Yeah, of course. And just hook it up the right way. So, yep. I would not worry about...
no precision rectifier required.
No.
You also add offset, which is annoying.
Although then... The thing is, though, then it always goes... You always have to put it in the negative line of your product. You can't put it in the positive rail. Because the positive rail can fluctuate a bit. Relative to... Anyway. No, because your current's always flowing through your shunt resistor one direction. No, that's fine.
All isolated.
Forget I said it. Forget I said it. Yeah, and it's floating too, if it's battery powered. But once you hook it up to your scope, it's not. And that's the other problem. Annoying. That's the other problem, right? Is that I thought, it should, ideally it should overcome that problem, right? It should overcome the problem of...
that's not easy.
No.
You need a linearizing...
You need analog isolation.
Linearizing optocouplers. So it's got a feedback loop for optocoupler, and you've got two precision matched optocouplers.
It's just... And there's bricks you can buy that do it, but your price has just gone through the roof, right? And there's another sneaky bastard way to do it is, really going to town, is you convert it first.
Oh yeah.
You send the digitally easy over the isolation, right? And then have a DAC, and then have a DAC output, right?
Yeah.
And that's actually.
Put a notch filter and kill that.
I would like
sample.
This actually. I'm gonna sit down. This actually came. I did think of this actually. This was one of my original ideas for a new microcurrent. Is that it would have a converter built in. Yeah. Right, so that you could either feed like a high, 24-bit or something, even though they're 18 bits effective or whatever. But
and
still,
$18 per part.
And $18, whatever, right? Cost really isn't an issue for a high-performance niche product, right? To a point. And so put like a high-spec converter in there. One of the, I was thinking one of the sound chips, one of the ones designed for audio.
Oh, those people.
But they're not high, but they're still not high enough because they're... I think they can, they can't do a couple of 100 kilohertz bandwidth. They can do audio, some of them do up to 50, some of them might even do 100, but the current microcurrent is 330. Yeah. K
and I don't know,
bandwidth.
Because you need a stage after the DAC as well if you did it.
Well, see, here's the thing, right? So I thought it'd have dual functionality. It would, once you feed it into the converter, and you convert it, you get the high dynamic range, so then you don't have to necessarily worry about range switching. No. Right? There's no auto ranging stuff to worry about. If you can nail the high dynamic range, if you can solve the problem that way, you solve it. And then you just choose the range resistor to match. Yeah. And...
I might have a part, that's what I'm doing.
Oh, okay. So you can... So once you've got it in a converter and you solve the dynamic range problem, then you can output here's the thing. You can both store it, or you can feed it out via USB. So you can have an application that reads it, but then you've got the same grounding issue. So that's why you can record it and you can record it, like you can operate your product, and it stores it, and it samples it, and then you upload the data and analyze it.
Yeah. The problem with the USB thing is, which I've come into recently. Is isolating USB is the world's biggest pain in the ass.
It is.
It's not at all. It's designed like. It seems like they're trying to make it impossible. It's
not a pleasant
like
thing.
Analog devices. I think it's analog. Maybe it's linear. They make an isolator for it. Nice picture, right? Yeah.
Is that okay? Is that a waterfall?
Yeah.
Is that in Zion? No, that's not in Zion. No.
I will say that this is automatic from Microsoft.
Automatic from Microsoft, so you have no idea. Okay.
Not a clue.
Sorry.
And I turned off the blurb that tells you. So if you want to isolate USB, it's very hard. Like analog devices failed to do it. They have like a 10 megabit. You sacrifice 480 megabits per second down to like 10 or something through isolation.
Right.
That's like in the order of magnitude correct. It's actually wrong. I couldn't be right. But isolating USB is the world's biggest pain in the ass unless you go spy.
Yes. Yeah. Yes. So.
Did I type my whole password?
Yes. The ADAM devices they're called. ADAM.
Yeah. Good memory, man.
Yep.
Yeah. Yep. I've commented on Dave's part number memory before. It's ridiculous.
It's very selective. It's a very selective.
How do you
memory.
know that?
It's a very selective memory. I've looked at those parts quite a few times.
Yeah.
The ADAMs. I can't tell you the number after it. Is it a ADAM 600?
I don't know. I saw it like 2 days ago. I don't remember.
Yeah.
He's probably seen it too.
They were all the rage when they came out. When they first did they advertise them in the magazines back then? It was like
extremely useful.
Yeah. Very, but they're very pricey. They're like $30 chips or something.
Yeah.
They're like,
So if we were to isolate USB, that's tough.
Yep. Because I was actually going to have a product that just did USB isolation. There's a few on the market now.
But they're all bulky. They're all like all of them.
Yep.
I've been looking.
Yep. I know. Somebody's sending me one in the mailbag. It could even be sitting here. I've got a USB isolator. So
they're super useful.
Yeah.
Where's this?
But all it is basically the ADAM chip and power supply. Like that's like power. Like although no, don't the ADAMs have the power coupling from one side to the other?
Yeah. They have an integrated converter.
Yeah.
Yeah.
Yep.
Ridiculous stuff.
Yep.
It's up to level ridiculous.
Yep.
Where's this ADC? It's 16-bit actually. I've just remembered.
Did I tell you I got a license for Circuit Maker?
That is so cool.
Yeah.
That is so cool.
Oh, sorry. Yeah, Circuit Studio. Well, it may not be cool if it doesn't work very well.
I like it.
Yeah. Well, it's strict. You've used Circuit Studio. I'm not talking Circuit Maker.
I've used Circuit Studio.
You've used Circuit Studio.
Yeah.
It's a stripped down AD, so it works all right.
Yeah, it's fine. But you know how I am. If it doesn't have that feature that slows me down a little.
Yeah, it slows you down a little. Yeah, I know.
That software's dead to me.
You're right. Right. So anyway, they got me a free license. I'll start using it.
Okay, here's the part. So the ADS8330 is a very good part. It's 16 bits, so you're not getting it's greater than the standard.
16 bits isn't enough.
Standard's like 12 though.
16 bits isn't enough for the dynamic range. I've done the math before.
Oh, really?
From the top of my head, 16 bits gets you from. I don't know. You can do the math now if you want, but it doesn't get you from. It gets you from 10 nanoamps resolution up to a few milliamps or something. It's like it's not enough.
There you go.
It's not enough. So, so I'd be looking at like maybe a high performance 18-bit converter perhaps.
There's a lot of these. Like you can oversample this type of stuff.
Yep,
like
and that's 1
meg. Yeah.
1 meg sample.
Yeah.
Right, so 500k bandwidth.
Yeah. So what I'm using in this project is oversampling.
Oh right.
And because I have Gaussian noise,
okay.
It's inherent in the circuit.
Okay. Right.
Lower noise power supplies don't always make things better. You can use them. You can use Gaussian noise to your advantage with.
Gaussian? Is that how you pronounce it?
I've only read it.
Gaussian.
Gaussian.
Gaussian is how I have always pronounced it.
Yeah, probably right.
Gaussian.
I've only read it. So, I don't know, people probably said it at the
Young
times.
whippersnappers.
Gaussian. No one corrects me, so
Right.
that's I hate not being corrected, right?
I've got a friend who, when we were young, he used to call chassis, like a chassis, chasis, because that's how it's spelled. That's how it's spelled, right? And I called diodes. I think I said this before. Diodes when I was like younger than 10, by the way. So don't judge me. It was a diode. I didn't know. I've never heard any, because I didn't know anyone who did electronics. I was in my own world.
Yeah.
It was me and the word on the paper.
Yeah.
And it was a diode.
Yeah.
So for years I called them diodes.
I called stomach.
Stomach.
It was clearly spelt stomach.
Yeah.
Or stopmac.
I cannot remember the first time that I heard or found out how you pronounce diode, but yeah, I was quite embarrassed that I was calling it diode, but I didn't talk to anyone about it, because my parent, I'd say to my parents, and
no one can relate.
They didn't know, they didn't care, so, yep.
So would you want to oversample? Like,
Nah.
Okay.
Yeah,
Not a good converter.
I'm not an oversampling fanboy.
It's alright. You can increase the effective number of bits by about 2, 3, 4 if you really don't care.
Anyway, nah, brute force.
Yep, fair enough.
Anyway, still don't know. You really have to try it, whether or not you can get a suitable converter at a suitable speed. Like, I'm talking 1 megahertz plus. So it's got to be maybe several megahertz at least, sampling rate, to get, say, 500 kilohertz bandwidth.
I haven't set up your Wi-Fi yet. So I can check now. The reason I got this one was because it has like great reception. I can get 2 bars inside a steel elevator.
Nice.
Yeah.
Sweet.
It's like level ridiculous. Anyway, DigiKey.
I can confirm that mobiles do actually increase their output power when you've got no reception and you call the emergency number 000. I think they actually increase the output power of the phone. Wow. Because I was stuck in a lift here in the building. I got stuck in the lift and I could not get reception. And it wasn't just like, and Telstra is the best reception here, and that's what I've got. The others simply don't work at all.
Yeah.
So it wasn't. I know that when you dial, not 911 here in Australia, by the way, it's
000. But
000.
we still get. I think 911 was called so much we redirect.
Do we? I don't know. I've never tried it. Anyway, and you can do 012 as well, which is the emergency. Yes, 012 is actually the emergency number that will use any network.
Neat.
But then so does it's fairly redundant, because then so does the 000 as well. Yeah. It does that. So anyway, so it wasn't using another carrier. It must have been increasing the output power.
Well, it should.
Yeah, it should.
Set fire to that antenna.
Who cares? Yeah, who cares about specs and government regulations? No, you're in an emergency. You want,
Or for the matter of the integrity of the phone antenna after you finish.
Right.
So set fire to it. I don't care.
Anyway, the reception was perfect inside the lift, which I could never get reception in. Yeah. That's with any provider. So yeah.
That's marvelous.
Yeah, it's great. It worked.
Okay. So we're going to get the result of your thing pretty fast. So what do you want? 1 meg?
No. We need faster. Go for 2.5.
That's way up there.
Yeah, I know. It's a specky part.
It's level ridiculous.
Yeah. What converters are you searching for? What bits?
20, above 22.
Oh, above 22. No, go from 18 onwards. 18 might be enough.
We do have a part,
Sorry?
We have a part.
Oh, yeah.
It's $52 per part.
Yeah, $52 in one-off. Yeah, thank you very much. Yeah.
I'll open it. Number of bits. I love the new DigiKey. You can delete parameters.
Yeah, what's that 125K?
Oh, probably aggregate.
Yeah, okay.
It's many channels or something.
And that one's only 16-bit. 16-bit, 2.5 meg.
Okay, so how many bits do you want? 18 above?
18 and above, yeah.
There you go. Let's see what we get. Is it possible?
I think there's you can get like 12, like, because the
that was actually the best value part.
Yeah. Oh, really? The what's the?
Yeah. $36.
Oh no, it's 16-bit. Sorry, I'm looking at the red Pattaya. The red Pattaya samples at 50 meg or something, and it has a,
Right.
I think a 16-bit converter or something.
Yeah.
It's pretty schmick.
There you go.
Yeah, no, I know it's leading edge.
It's got all the stuff you want.
That's 24-bit. No. Yeah, no, Sigma Deltas, no. I doubt it's getting that high. I think the DigiKey might be wrong there. I'm second guessing DigiKey here.
Let's have a look.
Will I be right?
Willie, I'm gonna bet no. I think DigiKey's right. It doesn't over the what?
Yeah, but no, you saw the bandwidth on there. It had like 125k something.
I think that'll be, it's many channels, isn't it? So if you're using each channel, you get that for if you use all channels.
Where's the
on
data
a number
sheet?
of inputs. Okay, this is more confusing.
Where's the data sheet?
Here it is. 4 mega samples.
4 meg samples per second.
Isn't that another number?
103 dB of dynamic range at 4 meg.
Okay, there you go. So you just get a bit more dynamic range.
At 120. Oh, that's why they had 125k in there, is because they have two specs. One at 125k for audio, one at 4 meg for
Here we go.
automated test and measurement. Yeah.
The device offers 2 speed modes with a distinct interface, resolution, and feature set. In the high-speed mode, the device can be set to operate at 4 megasamples or 2 megasamples. In low-speed mode, it can be set to operate at 1 megasample, 500 kilosamples,
Yep.
250.
That's not good enough, so we want the high-speed mode. Yeah.
Yeah. Still good.
Yeah, yeah. Anyway, so we can use, that's the pricey part, but we might be able to get quantity.
It's okay.
Anyway, anyway, that has to. So that's one way. That's one version of the product that, I don't know, is it advantageous? Like, you know, like a scope is nice, but I think there's another current measurement tool on the market that you hook up to a PC, and.
Well, I'm sure that there surely is.
But then you've got to write software to go along with it, right? And you know.
And then every other person's going to request you integrate it with all their tools.
Right.
They're going to want it to work with MATLAB and National Instruments tools, and then they're then they're going to want a Python library. You're going to get that very quickly. And
anyway, here's the other part two I was going to get onto. If you went for an ADC, we weren't supposed to be talking about ADCs and all that crap here, were we? We were supposed to go auto-ranging, but we've gone away from that. Once you've got it sampled, then you can, you can USB isolate it easier. Yeah. So you can hook it up. Probably wouldn't want to stream that data in real time.
No, you've got to buffer it.
You've got to buffer it, right.
You've got to buffer it, because the USB is not real time anyway.
So you don't even need USB. You can save it to an SD card. Right, you can just have a little SD card on the side, capture
which is isolated.
Which is isolated, exactly. Just hook it up.
Yeah.
It'll have a capture button. Maybe it'll have a little LCD telling you what it's doing. You know, maybe changing some modes and things. You know, how much space you got left on the card. Blah 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 blah. And it wouldn't be able to write to the card in real time, would it?
No, buffer it again.
Buffer it again, right? But anyway.
Well, no, it probably would. Not at 4 megasample. Not at the full sample rate.
No, you'd have to buffer it. So you'd have to...
Actually, what speed did I get? SPI.
See, now you're getting real fancy, because now not only do you have a converter in there...
You've got a logger.
You've got a logger. You've got a micro. You've got DDR3 memory to bloody... Or not DDR3, but, you know, you've got, like, large amount of memory. Like, you couldn't use SRAM, for example. Yeah. Right? So you go to DDR memory for the amount of memory you need at 4... Well, at 4 meg sample...
You don't have to. You can use FRAM.
Yeah, you're an FRAM fanboy, I know.
It says, you don't have to wait. No waiting. Right. I love it.
All right.
Yeah.
Could be FRAM, all right. So, these FRAM fanboys, I don't know.
They're so low power, it's ridiculous.
Anyway, that's, neither here nor there. Unless you're a fanboy. And then you obsess over it and go to bed dreaming about
I'll be happy about the next technology that does the same thing.
Right. All right, now, so you... What? Hang on. Where were we? Got too many side parallel talks going on here.
Well, the buffering.
So many directions.
So
buffering.
Do we need to buffer?
So yes, you would need to buffer at 4 meg sample per second. So that's meg samples. So however...
It's 20 megahertz clock rate. Divide that by 8. Oh, actually, divide that by 24.
Yeah, because we're talking 24-bit samples, right?
And then you get a tiny bit less than that, because the start of a block, right?
Yeah, right. Anyway, so we're talking very significant amounts of memory, and you want to do it for record for a minute or something, you know.
You'd only be able to do about 1 to 2 mega samples because, 125 divided by 24, you're getting near 1.1.
Right.
Yeah, exactly. Right.
Right. Anyway, the conclusion is you need a lot of memory.
A lot of memory, very high speed.
Right. So you need it. So the memory needs to be DDR memory.
Pretty much.
Right. Well, it needs to be dynamic RAM. Right. Static, you're not going to get 100 meg or you're not going to get hundreds of megs worth of static RAM. Right. So I don't know. I haven't looked for a long time. Can you get a 1 gig static RAM now? Probably.
Yeah.
I don't know.
Yeah, I've
I don't know. Anyway, I like static. I'm a static RAM fanboy because they're just much nicer.
SRAM.
And 4 meg is not fast. I mean, that's nothing, right?
SRAM maximum.
Oh, you just Googled X-ray.
Well, I was getting another one. 1 GB, 1 gigabyte.
No, just go into...
There we go. Yes.
Did you key? Yeah.
The answer's already a yes.
Yeah. Oh, yeah. Yeah, 1 gig, 4 gig SRAM.
Yep.
No, it's DRAM, dude. It's DRAM. DRAM, Integrated Silicon Solutions. No, it's DRAM. Yeah, even the URL is DRAM. No. Anyway, it doesn't matter. That's totally details. We don't need to know about that, right?
That's true.
So we buffer it. And then if you buffer it, right, you can either save it to an SD card.
And then you block write when you're done.
Whatever. Yeah, of course.
But then that takes the time it took to write plus...
That's all right. It doesn't matter. It's a one-shot deal. This is a special purpose application. You're not doing this 1,000 times a day. You're doing it, okay, I've got my product. I want to measure its power consumption. I don't care if I have to dick around for 10 minutes to do it. I'm going to do it. Right? And it logs it. It logs it all. And then, so once you got that, you can save it to an SD card. You could upload it via USB, but then you got to include USB and drivers and shit.
Well, if you upload it after the fact, you don't need to isolate it.
Yeah, no.
So
exactly. You got to disconnect, but then people will plug it in. If it's got a USB, people will leave it plugged in and blow up their product. Right.
That was I just remembered.
That's a DIMM module.
Yeah, I know.
What?
Still SRAM. Apparently.
No, that's wrong. No. No. Oh. Really?
Like maybe we could just.
Anyway, maybe it's out there.
That means.
Okay.
That means that you can get a.
It doesn't matter.
Module.
Storage solutions don't matter. Stop looking at storage solutions.
Well, it could make it impossible.
No, it doesn't make it impossible.
Yeah.
Storage solution. So once you've got it stored, you can save it to a card, sneak and edit across to your PC.
Yeah.
Or you can upload it via USB. And here's the other novel thing, is that you can feed into a DAC.
Yeah.
And you can output it. But how do you get the dynamic range, I hear you say, on your so you can see it on your oscilloscope instantly. How do you get the dynamic range?
How do you get the dynamic range?
Logarithmic.
Yeah, okay.
So, yeah, it's a logarithmic function. You can do that.
So output log in DAC.
Yes, so you can set your... Yeah, so you can set your... Well...
Then you definitely need a micro, right?
Oh, yeah, no, it becomes... Anyway...
A high-speed micro.
Just to see it on your scope, it's kind of pointless to add that extra hardware when you've got the data and you can just go view it on a PC. And you can have a PC app that does everything. It can have cursors and you can... I
guess it's just the minimization of desks.
You're right, yeah. But it's a special purpose tool. It depends how you market it, right? It's no longer marketed as a burden voltage to overcome burden voltage on a multimeter.
It's a second product, different product.
It's a totally different product. It's niche, It's the micro monitor or something, It's the, It's entirely different.
Yeah.
And then that doesn't take sales away from the microcurrent.
And it doesn't necessarily have to have the same burden voltage spec. So which might make things somewhat easier with
still, it might, but
with the gain.
But you do want a lowish burden voltage. It may not be as extreme as the thing.
Yeah.
But then again, once again, you'd have to do the math based on what's your maximum input current, and I don't think we can. You definitely can. I guarantee you cannot get from, top of my head, you cannot get from nanoamps to amps. You can't go that far. You can go from nanoamps to milliamps, maybe, with your 24-bit converter and 18 effective bits or whatever it is. And you just, Do we have a calculator?
Yes.
Yes, we do. It's the EV Blog Lab. They're never... I've got like 20 calculators in this lab, I swear. And, no, that's a... That's a 4-banger. It's not even a scientific, is it?
I could change it.
Oh, dude. That's disgusting. Get that out of here.
Alright, it's out.
It's disgusting. Alright, I got my crusty old one. This is the original one I had in... I'm not going to say high school. We weren't allowed to have calculators in primary school. Did you have calculators in primary school?
No. Although,
I'm impressed.
I don't have a good memory.
Okay. All right.
I don't think I did.
Now, so let's say what's 2 to the power of 18? Let's say we've got ourselves a 18-bit converter. So 262,144. I should know that. Okay. I could count up in powers of 2 to...
I started with 65,536.
Six.
Then I times it by 2 twice.
So, right. Okay. Yeah. Right. So if you've got, say, you want, let's say, 100 milliamps full scale. Yeah, let's be.
Are you giving a gain?
Let's be generous and hang on. So if we've got 50 milliamps, right? Let's just say 50 milliamps full scale. That's our product's full scale capability. Divided by our number of bits. It's 190 nano. There you go. So we get in there. So I was in the ballpark.
So
I was there to an order.
Per bit you get
190 nanoamps per bit for an 18, assuming you've got 18 true bits. That's why I'm saying even with the 24-bit converter, your effective number of bits is going to be like your...
What's the maximum accuracy? So what spec do you want? So
well, that's another thing. That's another
because that changes the bits.
Yeah, I know. It's
one.
I know you can't. Yes, you get
one on your spec is your
accuracy
minimum bits.
Your accuracy is way off down at the low end.
Yeah, because it's one on the bits.
Yeah,
right?
it's
one on the spec.
It's crap.
Times 100.
It's going to be crap. Yeah. It's going to be crap. So you can get the resolution.
It'll probably be okay.
But there's a big difference between resolution and accuracy.
Oh yeah, way different.
Yeah, there's a huge difference. Like if you just want to see your waveform.
One's logarithmic.
Yeah, I know. It's just like, yes, it is not accurate down at that 190 nanoamps.
Which people don't realize.
Yeah, I know.
People don't realize they have controllers for things, and they're trying to control around like 10 millivolts.
No.
And it's like you've got like 10% accuracy.
No. If you're lucky.
Yeah.
Right.
The reference is like a volt.
Yeah. No, it's just, well, by definition, you have 100% error on that 100, and you have plus minus 1 bit, one least significant bit. By definition, you have 100% error on your 190
it's halfway
nanoamps.
on either side.
It's like you're gonna, at best, it's halfway on either side. Like, it's just, no.
Yep. So you want 10%? You got 10 bits of it.
You need 10 bits. Well, you need 10 least significant digits.
So for 1%, which is probably your product spec, times that by 100, I guess.
Oh right. Okay. Yeah. So you could.
So 19 mic.
Yep. Yes.
19 mic for 1%.
I think that's right. Yeah.
Yeah.
Anyway, so it's like it's bugger all. So that kind of you can't.
Well, I guess at that
have
range,
your cake and eat it too.
You would probably change the range at that point.
Here's the thing. You either have auto-ranging, which increases your accuracy by orders of magnitude down at the low end. But then that introduces the problem with auto-ranging.
Here we go, on the topic.
On the topic of auto-ranging.
Yeah.
Regardless of how you implement your auto-ranging, and there's several ways to do it.
Yep.
You are going to have, you're going like this, and then you've got, a big spike of current like that, which you try to measure, and then it's going to drop down, and you're going to measure the small amount of current in your sleep.
Yeah.
Right?
And it would auto-range at that point.
Yeah. You have TD, dead time. You have dead time. Is the battery still working in my microphone? Bar graph's still going.
Which, if Which if your sleep is a small period of time, and it goes back on, you miss entirely.
You miss it entirely.
Yeah.
So it's got to be quick enough, right?
And it's probably the exact inverse, but
because you don't want a result that looks like that, and that's not, you don't want like a big false spike in there, or you don't want a big false spike
and it will do
here.
That.
Like you want
auto-range will do that.
Yeah. So your circuitry needs to know I'm about to auto-range, clamp the voltage, or hold it, or don't sample these bits. Like literally turn off.
Put a sample and hold there, and then short the output to the other circuit.
Yeah, and then you design this in so that you know how much time it takes to switch, based on straight capacitance and everything else, right? So I know it's greatly disturbing. You figure out how much dead time you've got, and build that in, and that's part of the spec for your product. During switching, there's some dead time. We don't want to show. The worst thing you can do is show spikes and other things which aren't really there, because you don't want to show a waveform.
Or even worse, because of the dead time, you have most of the time a micro is in sleep, right? And it does a burst power.
Oh,
and if it latches on the negative.
Is there someone at the door? No.
Like if it latches on 0,
that's
as close as it can get, because power is immeasurably low. And then it peaks up. It's dead for that time, goes back down, it goes like this.
Yeah, right.
Like nothing happens.
No, I know.
And then when it goes back down, you might actually get the auto-ranging kicking in because of delay.
Yes.
And then you'd be like, noisy for suddenly. And
No, and if you're in there at for want of a better term, a beat frequency of your auto-ranging dead time and recover and switch on versus the microcontroller, you could actually, if you could adjust the dead time on your sleep time in your microcontroller to match the dead time, you would actually, you could
draw a picture. You could
your auto-ranging circuit would just go.
Yeah, it wouldn't.
And
you have to be able to digitally adjust auto-range.
That.
You can't do it with window detectors.
Yeah, no.
Because the whole circuit has to be completely aware.
Yep, I would. Yeah, I would put in. I just put in dead. Like if it was like this, I would just put in the last known data and just insert it for an extra 10 samples or something, and then rather than because you can't put nothing, you've got to extend it out. I would just say it's extended out, and then. Okay, if you've got a fast spike, you're going to miss it, but that's part of the spec of the product.
Yeah, digital sample and hold.
Did you know that the Fluke 87, don't know if they've fixed it, had auto-ranging problems?
Really?
Yeah, it'd hunt. I remember you hook it up to a mains transformer would do it. Like I had a specific mains transformer, like you measure the primary of a mains transformer.
It was auto-ranging too quickly or something?
Yeah, it would. It was too close to the borderline value, and the auto-ranging algorithm just would hunt between ranges.
Hysteresis.
Yeah, it would. Anyway, I don't know. It was maybe the inductive element, cause current through the inductor, and that was causing. But it would cause the auto, and no other multimeter did it. The Fluke 87 did it.
Wow.
Yeah. It was I had it a couple of times. Not every mains transformer, but I think there's 2 that I've ever measured have done the same effect. Have caused it just the right value, just the right amount of inductance to cause it to. Anyway, so it would never display anything. It would actually display 0, 0, 0, and you can see the decimal point just keep hunting back and forth on the Fluke 87.
Yeah.
It's supposed to be the bee's knees.
I must check the time.
Oh, yeah. What time do you?
I think it's at 5. I'm good. 5:30. I have to be in Hornsby. I'm fine.
Okay. Well, you want to leave here before 5.
Yeah, definitely.
Yeah, because you'll get caught.
Yeah, I'm gonna leave at 1:45.
Yeah. At best.
Yeah.
Yeah. All right. So, we're not going to run out of tape. Now, I set this to deliberately low resolution. So the resolution, not low resolution, low bit rate, 5 meg samples per second. So it's just going to be pretty. But there's nothing moving. So the low bit rate's only a problem when something moves. So there you go.
I've got a dialog box on my head.
What?
See on the camera?
Yeah, you do have a dialog box.
I've been trying to see whether I look like I'm looking at the camera.
Oh right, and you can't see it because you're got a mask on.
Box on.
Yeah. That's disturbing.
Very.
Anyway.
Yeah. So.
Check. We're still good on the mic. Oh.
So if we did a micro, we can
peak. Sorry. For headphone users.
Yeah, so if we did would you want to do a micro for that hold? So, because if you are, you're using an ADC and then DACing it again, or
I don't. Yeah.
Otherwise, you do a manual sampling.
Well, no. Well, we have to use a micro. If you're using an ADC, you've got to feed it into. If you aren't streaming it straight out of USB's clacker, you're sampling it. So you've got to have a micro.
Yep.
So it's already there. So we would do that in digital. You'd just go, right, I'm changing ranges. I know when I'm changing because the micro is doing the range. Or micro doesn't necessarily have to do the range changing.
No.
But it can sense that.
It needs to be entirely aware.
Yes, it needs to be entirely aware that it's changing.
Almost, it needs to be aware before the circuit kicks in.
Before the circuit kicks in.
Which you can just handle with propagation.
Can put in a little delay.
Yeah, you can put a delay.
Propagation's not going to do it. The micro's not that quick.
Oh, I mean, like add a.
You're talking add a microsecond or something.
Yeah.
Right, add serious business so that you have a
like
couple of cycles to
inductor.
detect. Right.
Like put a ferrite bead in the thing or something.
Although there's no reason why it couldn't interrupt the micro.
No.
And say, I'm switching now, interrupt, and it stops. I don't know.
You do still always get that. There is always like 100 nano.
Yeah, yep. There's a dead time. There's a
micro.
a finite amount of time there.
Yeah.
Yeah. This is annoying. Anyway, so I don't know. That it all comes down to, I hate to say it, marketing. It comes down to what target market you're trying to meet, whether or not you have an ADC in there and you sample, and is that the market you want to go after, or is it, do you want it to be a microcurrent Mark II where it just does auto ranging and outputs analog and then leave it up to the person to sample it, or
they view the multiplier. Yeah.
The problem is, so if you can, that's the thing. You either solve the dynamic range problem, we said this before, you solve that, or you solve the auto ranging problem. Both, the auto ranging problem, the dynamic range problem you can't solve externally to the product. It's got to be built in to the product.
Yeah,
well, both of them have to
it'll peak either way.
Both, have to be built in.
Yeah.
So, because you don't have the noise floor. You can't have only 5 volts out maximum, which is, and then have the dynamic range, to get down there. It's just...
You're saying you can't...
It's down in the noise.
To saturate because the rail's noisy.
Yeah, it's just... Yes. Yeah, it's just...
Especially if you have an ADC.
It's just not going to work. Yeah. So you either solve it right there at the point that you're measuring it, or you don't do it at all. Or you simply have, it's a microcurrent Mark II and it's just has auto-ranging niceness on it. I don't know.
In which case, it's got to be digital.
Does not have to be digital. You can do auto-ranging entirely analog.
Well, there's problems with the multiplier.
With no micro.
You can do it with window detection and whatnot.
Yep.
Or just threshold detection.
Oh, threshold detection. Yep. I say that a lot. Actually. When I mean threshold, I say window.
It is a window. 0 to.
It's a one-directional window.
Yeah.
No, it's not a window. No, there is no one-directional. What am I talking about?
It's from 0.
Right. Okay.
Yeah. On the if you do the threshold detection, auto ranging, multiplying is only 8-bit.
Multiplied.
If you multiply the output range channel with the output current channel to get the actual current, then you're multiplying 2 8-bits together. So you're killing your effective accuracy.
Oh, I wouldn't bother doing that. I would just output what current range you're on.
Just with a coarseness for someone to be able to see it.
Yes.
Okay.
Yes, that's it. And then leave it up to them. But then it's not a polished product. If you have 2 outputs, as we said before, one to show that it's overloading or one to show which range it's on, for example. And then you hook that into your scope and it's okay, so you've got your current waveform, then you've got another waveform on channel 2 that shows which range you're on, but then you've got to figure it all out in your head and it doesn't give you a nice...
And if you've got 6-7 hours of it, it's too...
It's not a nice polished product.
And then it's to digital.
Yeah.
Because you need processing.
No, you don't necessarily need processing. It can be entirely analog. I guarantee it. That's like in my eye. hang on.
I'm going to move so I can see my... Oh, that's it worse. That's worse.
Got it, I think. Anyway. Yeah, I really need to think about...
Well, we need specs. You need something to achieve, because otherwise...
Yeah, I know, which comes down to
otherwise
which
you can
target.
go to any... Otherwise
I
you
know,
you
can go, yep.
directions.
And it starts with the target market. What is your product trying to achieve? Do you want a really nice, elegant solution that just targets current monitoring in modern low power products? And then you go, okay, if it's the keyword there is low, you don't care about the high power products. You don't have to worry about amps range.
No.
Right?
Which
because
is a huge like.
I know,
like,
it's big. Yeah, it's a big deal to go, I'm not going to do amps.
Yeah.
You know?
But like the market is huge in the small range.
It is.
It's bigger.
That's what everyone's...
Much bigger.
Microcurrent, don't have one. I can't even flash it around. Anyway, it doesn't matter. There we go. No, look, it's sitting right in front of you. There. On the shelf. Second shelf next to it. Yeah, there.
Oh.
All right. This was originally designed like 9 years ago or something, simply to overcome burden voltage on a multimeter because I was having a problem with that at the time. And I thought oh yeah, that'll make an alright article for silicon chip, I'll do that. And that was it. But, like, overcoming burden voltage. So I thought, that's what it's used for. And I only did the nanoamp range because I could. Right? It was like, I didn't have an immediate need for the nanoamp range. You know, one...
You had one
millivolt
range
per
more
nanoamps.
than you needed,
Yeah,
one
I
range
know.
less than you needed.
It just like... And then everyone bought it for low power product measurement. They go, like, this is the de facto tool in the industry for measuring low power. Yeah. And because it's very accurate too. It's like, you know, it's the de facto tool, even though it's a bit clumsy.
And if that's what they're using it for.
That's what they're using it for.
Then
like,
what is the next logical step? Bandwidth, maybe?
Oh, a higher bandwidth is always better. Yeah, this does 300k or something.
But what can you do? But you don't get a lot better with choppers.
No, you don't. I've done a whole video on this. If you I've cascaded 2 amplifiers in here. If you cascade 3, you might get 400 kilohertz. Like it's diminishing returns. You can put 10 op amps in series, all with lower gain, and your bandwidth, you might get 500 with 10, like, or 450. It's like really diminishing return.
Yeah, but at some point it'll be 401 instead
right,
of 400.
Right, so you can put in greater than 400 in the spec. Right, it's all marketing.
Yeah.
Oh boy. So, yeah. So if you just target it to those people, which is why, getting back to this. The micro front end, we were going to, I thought, have that case and just have, you know, a simple, cheap thing that just targeted low current. Like, I set up to 50 milliamps minimum, could be 5, maximum, could be 5 milliamps maximum or something like that.
Volts?
No. What?
Front end was volts.
Volts? Huh?
The front end was the voltage thing.
Yes, but no, I'm talking about a microcurrent version.
Oh, right,
in the
yeah.
same case. No, sorry, the microcurrent in the same case, reusing the case for a little niche microcurrent that just measured small currents. But then you come back to the same problem of dynamic range versus auto-ranging, you know, and like you can't... And I had these ideas of, like...
Just thinking about that.
Everything's
under 100 mic. Like, all the low power
If you're
products.
just talking about... Yeah, but they can...
But the ARM ones
are
higher.
Well, that's the problem.
If
you've got a spike, if you've got a Wi-Fi, it's spiking hundreds of milliamps, right?
Yeah, and like almost all the smartphone stuff, that's way above.
Mm.
That's
that's huge.
It's not low power.
No, they just have big batteries in them.
Yeah. 90 milliamp.
That's why they get warm. They get warm for a reason.
Yeah.
Because they're chewing current. So
that's actually a huge range. If you want to go up to 100 milliamps down to nano,
Oh yeah, no, it's
And you want
it's massive.
If you want
can't do it.
auto-ranging.
You've got to, I thought we'd have like 2 ranges, auto-ranging or something like that. Or maybe even just a switch, because this box already has a switch on it for the range.
Yeah.
So we could just do it manually, and maybe that's, a cheap-ass version of the microcurrent that has BNC output and goes straight into a scope, you know, and manual ranging. I'm not sure if auto-ranging is the solution for this.
Yeah, BNC may not be the greatest for this as well, because the BNC leads are highly resistive, right?
No, it doesn't matter. You would for the input, which is what you're worried about. You would have a thing, we've got them here. Yes, there we go.
The shelf, it's working.
It's working. Everything's within. So you get. You probably can't see that on the camera. We're not zoomed in enough. If you're watching in HD, yes. To binding post / banana plug. So you just supply one of those with it. I know it's not optimum, but you get to reuse the funky case, right?
Yeah, and it's also more compact.
Yeah, and you can use this for other things.
Yeah.
Or you can, if you want to use the BNC, you can make up your own custom leads, go straight into BNC, do whatever. Like, it doesn't...
Yeah.
Yeah. No, it's better. I think it's more versatile than having to redesign the case and put binding posts on it. So...
Yeah, okay, yeah.
Because
if there's no lead, then better.
No, no. So that's it. No, that's it. Like, it sits there, and that sits onto your scope, and bingo, you hook your wires into your product. Like, and then I got to thinking, well, the problem with the microcurrent, which Murphy will get you every time, and I've been caught using it myself. Murphy's got me, is that you set it to 1 millivolt per microamp, right? So you can get a maximum of 2,000 microamps out of it, so 2 milliamps before it goes full scale and clips. My product draws 3 milliamps instead of 2 milliamps.
Oh.
Right? And I've, like, my watch, my micro watch was a classic example of this. When I first did it, my micro watch drew about 5% more than the full scale of this product, right? Just over. So I could not use the optimum range to measure it, because it was the fixed range, and so I had to put it up to the amps, or you had to put it up a range, which is 3 orders of magnitude. It's 1,000.
The inverse of the sweet spot.
It's the inverse of the sweet spot.
Yeah.
It was just
sour spot.
I still get emails, people saying, I need to measure 50 milliamps, and this only gives out, on that range, it only gives out 20 milliamps or 2 milliamps or whatever.
Yeah,
it's annoying. So I got into the
I guess
thing.
that's the standard though. Decades.
No. Well, the other thing is to have huge number of ranges. You have 10 ranges instead of 3.
And
right?
the optimum number for 0.1% is like not a good number.
No, it's
the optimum range is like, what is it? Can't remember. Depending on the bits of your ADC as well.
Well, anyway. It doesn't matter. Here's the answer, right? The way it's always been done, you don't use a general purpose product like this. The way since before I was born, the way you measured current is you knew what your current was going to take, right? So you knew its maximum current, right? So you choose a shunt resistor that just gives you your maximum burden voltage under. You would choose it. You would simply choose your dial in your. So I guess it's like ranging, but it's infinite, because you choose the exact resistor you want, so you get the highest dynamic range that just includes the maximum current of your product, because you can measure, stick your multimeter in there, and you'll measure the maximum current of your product.
Yeah.
The whole is, what does it take when it goes sleeps and stuff like that. That's the big question. So. I thought, I kept picturing like they'd have like little plug-in, like, those blade fuse kind of things like you get in automotive, like, you could choose your own resistor. Yeah, for a shunt. You would choose your own, the person would make their own shunt resistor, and they would...
Well, that makes sense.
It makes perfect sense, because otherwise you've either got to have a 10-range instrument, and you still won't get optimum results, right? You'll still be pissing away some of your dynamic range, because it's...
Yeah.
It's 1% over a range that you want. So you've got to go up to the next range. So instantly you've wasted 9/10 of your dynamic range.
Yeah.
You've wasted 90% of your dynamic range. You've pissed it away because Murphy got you because your range is 1 milliamp, 10 milliamps, 100 milliamps. Your product draws 11 milliamps. You have to put on the 100 milliamp range.
Yeah, I guess that's where the big advantage of the continuous wiper was.
The continuous wiper.
Yeah, it's not.
Oh no, pot.
It's not a few ranges.
Right.
It's as many as you want, and that leaves you with a constant burden voltage too, or a constant burden resistance.
Oh well, you calculate how much burden voltage you want, basically.
Yeah.
Yeah. So there's all these mixed requirements in there.
Low power is common though.
Low power is common. If you just design something just to measure low power micros, like there's a niche product there. There's a niche product.
So like low power, and what kind of range?
Well, low power to me would be at least 10 nanoamps resolution.
Okay.
With precision. This thing has 1 millivolt per nanoamp. So on a 3.5 digit meter, which is pretty much the most you want to use it, 4.5 maybe. But if you go down to 0.1 millivolts, that's 0.1 nanoamps.
Yeah.
So this will do 0.1 nanoamps. That's too far. That's gilding the lily, right? That makes, like, you don't need to go down that low. Like, that's really neat. That's beyond niche. That's, you know. In fact, that gets down to the point where I still have a lot of people. This on its highest sensitivity range, nanoamps, you've really got to know how to take those measurements. You can't just hook it up and expect it to work. There's the Keithley Low Measurement Handbook. It's like 300 pages. You can download it. It's a PDF online. Yeah. It's 300 pages long or something, telling you how to do low current measurements. It's an art. There's art and science. You know, nothing in electronics is art, but it's it's all science.
Is that all Kelvin-y stuff? Or?
It's all and it's thermal voltage, and it's like there's so many things involved. Junction stuff, thermocouple junctions. You put two dissimilar metals. Solder is a dissimilar metal to your copper, right?
You got to cancel all the coefficients.
Yeah, that can generate. Just a solder joint can generate a thermal EMF, and right?
Yeah,
that's just nuts.
Yeah, too low.
Yeah, it's too low. This is bordering on too low. Yeah. Like, it's just, like, people don't need that. That's why I'm saying 10 nanoamps resolution would do the business. But you've got to be accurate. You've got to know it's 10 nanoamps, plus minus 1 nanoamp. Like, it can be 10% accurate down it. Like, it can be 10% accurate at 10 nanoamps and you'd be happy. Yeah. Right? You'd be happy.
Yeah, because whatever.
Yeah. No, you don't, when you're down that low, you're happy.
We don't have batteries that bad.
No, you are. Yes, you are very happy if you're drawing 11 or 9.
Yeah,
it's like you don't care.
No. So what kind of maximum? So processors can go like 2 amps.
That's the problem. Like Wi-Fi, right? How much does a Wi-Fi module
with GPS
take?
on?
Oh, screw I'd be happy to say screw GPS. I'd be,
Because then you need the amp range again. Yeah, so it's like 100 milli is...
That's the other thing. Do you leave that up to the person's multimeter? If your thing is drawing 100 nanoamps or 1 microamp in sleep mode and then's drawing 2 amps in operation, you're screwed. I mean, trying to measure that is just insane. Do 2 separate measurements. You measure your 2 amps when it's on.
Yeah.
And then at that point, right? At that point, you don't care about the area under the curve, right? You don't
because it makes everything so insignificant.
It makes everything so insignificant. You know exactly what I'm talking about.
It's the only thing you're measuring.
Yes, right. Yeah. It doesn't matter. But if your product is going to sleep once a minute or whatever, and drawing 10 microamps in standby because it's running an RTC or whatever, and maybe update an LCD. You can update an LCD with tens of microamps. A watch, right? You're designing a watch and tens of microamps, right?
Yeah.
During normal operation, and then it might beep or do something, so it might draw 10 milliamps.
Yeah. Right,
and that's the order, and then you do care about the overall area under the curve because that'll give you your average current.
Yeah, because beep will be 1% of your time.
Yeah, beep might be 1% of your time.
But it'll be 100 times the power.
Exactly, it's
So
100
it's like
times the power.
doubling your power consumption.
Exactly. So on average, so you want to accurately measure that.
Yeah.
So that's why I thought when I originally got the idea to put a little microcurrent, a little 2-range microcurrent or something inside this case, I thought if it had 50 milliamps tops, that'd be plenty. Like, who cares above that? Like, it's just get a different product, right?
Yeah, or do 2 in the same time.
Yeah. Yes, you can do 2 at the same time because the burden voltage of a high current thing.
Slow. You want parallel.
Hang on. Hang on. You sell 2 of these.
Yeah.
One does the low current. No, you can't. You get once again, it comes down to the dynamic range. Because if you put 2 of these in series and you have one in each channel of the scope, right, you could happily measure. Well, then you have a problem with your common Earth, but let's just assume that problem doesn't exist for a second, for hypothetical.
We've isolated it.
But, just with our expensive analog isolator.
It is the only way.
But
or it's full diff amp.
Oh god.
Diff amp's okay.
It's 4:20.
Yeah.
All right. So so assume that you could measure both channels. You've got to put them in series.
Yeah.
Right? The 10 amp one doesn't matter. Because when you're in low power mode, the 10 amp one doesn't affect it. The current shunt is 0.1 milliamps or 10 milliohms. Like, it doesn't matter.
Like,
but the problem is when your GPS turns on and you draw your amp, your other one is just going to burden voltage goes through your roof and your product shuts down.
How about?
That's why you need the auto ranging. What are we doing?
So you got 2 ranges. Switchable, 2 different diff amps. Output switch.
No, doesn't matter.
Analog switch on the output.
Because this is your DUT.
Yeah.
Assuming it comes from.
So this was the test load 1, test load 2, and it's all this one's low, so it's always in circuit, and you already know that value.
Yeah, but the series, they're
that's what I'm saying. But you know the value, so.
Well, that's what my auto range circuit was going to do. My auto range circuit. We should do this for the benefit of the peeps. If I had a 2-range auto, a 2-range auto ranger.
Yeah.
Is that the correct? Yes. Right.
Sounds weird.
Here's your input current. This one is 10 milliohms for your amps range or whatever. You don't give a toss about that when you're measuring low current. So you don't have that can stay in the circuit all the time.
No, because what's the other one? 10 ohms.
Yeah.
Like,
Okay.
Yeah.
Okay. Let's say this is 10k, right? And this one is 10 milliohms, right?
Yeah.
You can put them around the other way. It makes it easier for. Then you have a.
It's 1/1 millionth. It's like a millionth of it, right?
Yeah, but you have your MOSFET, drawing a JFET.
Actually, JFETs are better.
No, they're not.
Yeah, because you get 1 mic leakage current across drain source, when it's off. Yeah, that's the maximum.
No, MOSFET's fine.
That's the spec. Yeah.
Right, so you don't care. The 10 milliamps is always in there, but then of course you need you need a diff amp, of course.
Yeah.
So that has to go into a diff amp.
Yeah.
Whereas this one can happily be single ended, you know.
Yeah.
So this one can just tap off there into an amp, and that one can. Well, it's kind of sort of anyway. Doesn't have to be a diff amp.
Yeah.
It can be right, and then you short out. So all your auto ranging is doing one thing, and that's shorting out your 10k or not. When you get to a multiple auto ranger, it becomes a more complex.
Yeah, when you get
beast.
more than 2, the leakage, what I was talking about before, starts it affects things quite significantly. So if you have 2 of them shorting, and then it becomes, are you shorting in parallel or shorting in series?
We're talking 10k. We're talking 10k. Leakage is not going to be a problem with 10k.
Yeah, but one that's like a mega ohm, if it was volt.
You know.
If you got one mic,
No, a
leakage,
mega
it's got a
ohm
volt
is
across it.
no, a mega's 2 orders of magnitude higher. 2 orders of magnitude, as a rule of thumb, an order of magnitude. You know, the errors become pretty insignificant. 2 orders of magnitude,
Yeah.
you
It's
don't
small.
have to worry about them.
It's very small. But if you
no.
have them in parallel, you start adding the leakages together.
Leakages, no, I don't think leakages are a problem here. I don't think they're going to be a problem. I stand to be corrected, but anyway.
I have it on good authority from like all forums ever that no, not that I'm wrong.
Right.
That the data sheets are being overly conservative with their leakage figures. So you get 100 nanoamps on like the best.
Yeah, but okay.
And
yeah,
like
but...
100 at about a mic on standard.
Oh, sorry. What am I talking about? Oh,
MOSFETs.
shit. Yeah, no, you're entirely right. Yes, no, you're... Sorry, I was thinking about something else. You're entirely right. Because, yes. But you got to have a MOSFET to get the bloody current, to get the thing down, to get the... Right, you can't put a JFET in there. Because they won't have enough on resistance. The RDS on won't be...
That's right.
It's way through the roof,
Yeah,
right?
yeah. So, and that's why everything uses relays.
Yeah, I know. Yeah, relays are... Yeah, I know. Relays are nice, but they're slow.
Freaking relays.
I know.
And then you can't do this.
Try doing a low leakage... I've done a video on this. Try doing a low leakage relay matrix with hundreds of relays all in parallel. If you want a nightmare of a time, the leakage drifts when you fart halfway across the room. When you've got 100 of them in, like a relay, you think is open circuit.
Yeah.
No, it's 100 gig. Right? It's 100 gig.
I didn't realize what you were saying.
They actually have specs.
What you're saying.
They actually have specs, right? They actually have specs. It's 100. You know, it's like in the order of 100 gig because there's contamination inside the relay.
Yeah.
Blah blah blah. There's contamination on your PCB if you don't do the slots and everything else, right?
Yeah.
So or they creep up the side of the contamination creeps up the side of the package and like, right? So you think a relay
as salty air combines with the PCB
and we were using them in a salt air
path.
environment. We were using it in a salt air environment too.
Ocean?
Right, yeah. It was for seismic stuff out on the back decks of boats. And the temperature swings and So yeah, saltwater environment, temperature swings from, like Antarctic freezing to like 60 degrees baking on the metal deck of the boat.
You want that condensation. You've got to have that condensation.
It's awful. It's awful.
Oh, that's pain.
Oh, it's so awful. And and so you look at the spec at like a real high spec, low leakage relay is like 100 gig. They'll actually specify the leakage. Which sounds great, but when you whack 100 in parallel, 200 as I was doing in parallel in a switching matrix, that ruins your day. Yeah. It's just anyway. So yes, you're entirely right about the MOSFET. Sorry, my brain was somewhere else. But anyway, assuming that's solvable, you only have to switch the one.
Yeah.
Which is
one's okay, probably.
Actually, I'm tempted to say, in that case, you may not have to take care of any switching spikes, or you may not have the dead time, which we were talking about before.
MOSFET's so quick.
Yeah, and because there's minimum capacitance in here, nothing's gonna like. Oh, no, I don't want to say it. I don't want to say it. But
drain source capacitance.
I know. That's why I said I don't want to say it's not going to be a problem.
The can of worms around MOSFETs is large.
Especially when you're dealing with low currents, which is... Well, the microcurrent is ridiculous. That's why the Keithley have a whole low measurement current handbook.
Yeah.
That just goes to town. Art and science, measuring currents that low.
Yeah.
But this one wouldn't go that low. It would go, as I said, 10 nanoamps per least significant bit.
Yeah.
Or 10 nanoamps per millivolt. 10 nanoamps per millivolt. Because you're feeding it into a scope only goes down to a millivolt.
Yeah.
Right.
I have an even worse scenario with the MOSFET.
What?
So because you always have to maintain a constant gate source or gate drain, whatever you're trying to do, you have to maintain a constant voltage to keep it on. If the output is floating, you have to be following the rail, right? Or are you actually going to ground that terminal there? That'd be okay.
Oh,
actually.
the FET you're talking about?
Yeah. So that gate has to be like real constant. Is that actually grounded or is that a floating terminal?
Oh no, that's the That's the terminal.
So is that floating or grounded?
Oh, it's not grounded to mains earth. It's. Oh, sorry. It will be when you hook it up to the scope. It will be. Yeah. Yeah. It's common circuit ground. It will be.
So you have to follow. Because otherwise you're switching.
Nasty.
It's real nasty.
It is thoroughly nasty.
Yeah. Low current's like the hardest.
Yep.
Yeah.
And anyway, that gets a more complicated scenario if you have multiple ranges. If you have like 5 ranges,
way more. You need mixed topology.
Yes.
Because you need JFETs are the way because their leakage is in the pico. Oh, nano peak.
But that leakage is only of use on the highest range resistor.
That's right. Yeah.
All the others you can use. MOSFETs are probably good enough.
Yeah, easily.
So we didn't really conclude anything out of that, did we?
What do we? We don't know what we're trying to achieve yet.
No. We still have to. The goal is goal of this should have been brainstorming a product segment rather than.
So is that 100 nano to 100 milli?
100 milli that'd be a killer product.
Yeah.
Even if you got to 10 milli, people might be able to live with that. It's only for low power watches and stuff because then it'd do Bluetooth like. See, a difference between 100 milliamps full scale product spec and 10 milliamps is probably not a lot, and it's not as much as you think, because if you look at the applications, products are using wireless these days, right? So it's all about wireless. Everyone's obsessed with wireless. Internet of Things, watches, wearables, all that sort of thing.
About burst.
And wireless is, it's about burst, and it's about either the two solutions are Bluetooth and Wi-Fi, right? They're basically the two main solutions.
Yeah, and the others around it.
Exactly. So 10 milliamps will easily do your Bluetooth, will it?
Not Wi-Fi.
No, but it'll easily do Bluetooth. What's a Bluetooth module typically? People are screaming at us.
Well, there's Bluetooth LE and then there's Bluetooth.
Yes, and then there's regular Bluetooth, which might be more than 10 milliamps.
I'm going to Google regular
Anyway,
Bluetooth.
The analogy I wanted to make is like the spectrum analyzer, which I don't have here. But Siglent and Rigol, they've released all these low-cost signal analyzers, right?
Yeah.
Which frequency do they stop at? Below 2.4 gig. Because they know everyone wants to measure 2.4 gig. So they're going to, 2 gig, right, is be our maximum. They can, even though it's built into the product, it can do 3.5 gig.
That's bizarre.
Because they want to upsell you to the next model. They know that is a big, you want to measure, 2.4 gig, right? Wi-Fi and Bluetooth and everything else operates around that
bastards.
range. I know. So they deliberately spec them lower than that. And that's a thing here. You go, well, we know that Wi-Fi is hundreds of milliamps, so don't bother. You either do that completely and you go 500 milliamps, or you go, or an amp, or you don't do it at all, and in which case you may as well go 10 milliamps.
That's
or 100.
That's burst, I assume.
That's burst. Yes.
Okay, here we go. Health concerns. This is about the antenna.
Have you seen my pen from DigiKey?
Yeah, I put it in my eye by accident just before. But there's a moment in the video where I'm like, I didn't know what was going on. I was like,
oh shit, yeah, I just did it.
I know there's a moment for each of us.
And that's not even. Okay, I'm seeing spots.
Oh wow! Interference caused by USB 3 from Bluetooth. I guess the speeds are similar.
Oh, okay. What?
Yeah, just this whole wiki section.
Nah, the USB is just generating broadband crap.
Yeah, probably.
Yeah.
So, here's the power stuff. This is the output power though, so I don't know the efficiency of the antennas.
Oh no, I don't know. That doesn't tell me anything.
Yeah, because we don't know.
Doesn't matter. Anyway, we've got to call it quits. I guess we need some more. It probably needs some product research. See what other products are out there.
Yep.
I'll do this, and you can do this too if you like.
Yep.
And we'll.
Well, I've got stuff.
Try and come up with a target
now. With the stand.
But then there's two solutions. One is to go into this case.
Mm.
The other is to be a upgrade to the microcurrent. But considering I've just ordered 1,000 more of these microcurrents, I probably shouldn't. Well, I want to sell my 1,000. I mean,
but
it takes time. By the time I probably would have sold them all by the time.
Like even
if we started this design, it'll take forever to get through.
Whatever happens, you will take a hit in those sales.
Oh yeah, no, of course. In fact, I'm happy to completely eliminate sales of this if I've got a better product.
Okay, yeah.
No, that's fine. I mean, that's the whole. I might even gain more sales because people are upgrading from this.
That's true.
So
resells.
Yeah. I actually had that. I had my original microcurrent. People bought my original. It's the exact same, almost the same performance as this.
Yeah.
It's a bit higher bandwidth, but that's it. And it's got a short feature, but whoop-de-doo. And they went and upgraded because they liked it as gold. It's like, Yep. Anyway.
Marginally better.
That's it.
Yeah.
We didn't really get into the auto-ranging side of things. That was the original intention here, wasn't it?
Well, we got into some of the problems of auto-ranging.
Yeah,
systems.
Yep. So anyway, there's many ways to skin that auto-ranging cat.
I think the secret with auto-ranging,
because you can do active amplification, you can do active current shunts.
Switching amplification is easier.
Yeah.
Because you can guarantee the current going through it.
Yes.
You can guarantee all kinds of figures.
Yep.
So it's a bit easier, I think.
So you don't necessarily have to do the current shunt. You can do an active. What they do in some of the Keithley meters and stuff, they have zero burden voltage. They because they don't have a current shunt resistor, they have an op amp, and they feed the current. The current goes through the feedback resistor of the op amp, and it generates a counter voltage, and it cancels out your burden voltage.
Neato.
Yeah, it's Bobby Dazzler.
All
right.
Cool.
Catch you next time.